Okay, good afternoon, everyone. I've never come on to music before, so that is a first for me. As introduced, my name's Adam. I'm the director of the Systems Lab in Edinburgh. So we work primarily with Huawei's internal workloads, but with external customers as well, like ByteDance, Tencent, JD, etc. And I'm also a professor at Edinburgh University. So this talk will be semi-academic, but also I'll be talking to you about some of the standards and the open source projects that we've been working on at Huawei. Specifically, the focus will be on OpenEuler. So OpenEuler is Huawei's open source Linux distribution, and I'm going to talk to you a little bit about the hardware architecture changes that we're seeing that will power Agentic AI going forward. And that'll all be about sort of disaggregated hardware architectures. So let's start with that theme. This is an Agentic AI conference, right? So Agentic AI really changes the system model and the way that we think about writing applications. Firstly, Agentic AI introduces long-lived stateful tasks, and those tasks are interactive workloads. This is a shift from the way that we have been writing applications over the years. And the workloads themselves, they can be enormous. They span multiple machines, not just single nodes. On top of that, I think what we sort of seeing here in the industry is we're forcing a system rethink, like the way in which we're designing hardware and the applications that sit on top of that. And those hardware shifts that we're seeing break many of the assumptions that we have in the stacks that are kind of commonly used, so open source stacks for cloud, and particularly the operating system. So I think this is probably one of the first times we've heard about operating systems during this conference so far. So what does this really mean? And why do I think that it breaks? So the current old model, if you like, the traditional model, what I'm talking about specifically is server-centric infrastructure, the way that data centers have been designed for decades. So this is a single node, and you need lots of these for your data center. Here you're seeing you've got some kind of network interface card, CPU, memory, some kind of accelerator, GPU, NPU, if it's Huawei, storage, SSD, etc. And of course, we're building data centers, right? So you might have thousands or you might have tens of thousands of these that are deployed into a single data center. And the way you get them to work together typically is that you have a large-scale cluster manager. So if you're Google, it will be something like Borg, or you'll have Kubernetes cluster manager that coordinates all of these single nodes together so you can run your workloads across them and splice them across the different hardware that's available. So why doesn't that work well for the agentic model? Well, in the old sort of systems here, current limitations, everything is organized around machines, right? So the resources themselves are bound to machines, and then you have to splice the workload across those machines. So typically this is a scheduling problem, and at cluster scale, this can lead to things like resource fragmentation, underutilization, etc. What you want with agents is something that's organized around the entire system. So you can pool all of those resources on demand given the workload that you have available. Let's have another look at something else. So you have expensive RPC communication. So remote procedure calls that kind of between the machines and also the cluster manager itself as the way that our current systems are designed. And again, what you want with Agentic AI is something like low latency access between the machines and direct sort of peer-to-peer communication between those machines. On top of that, data is constantly moved around between those machines. Ideally, what you want is the workload to be deployed next to the data, not shifting your data directly to the workload itself. This is a sort of an age-old argument that we're seeing across cluster systems. And then short-lived tasks versus kind of long-lived stateful execution as well. So Agentic AI, I'm going to argue to you a little bit this afternoon here, it requires a fundamentally different system model. So what does that system model kind of look like, and what are the requirements? So shifting out from a server-centric view to system-wide execution. First of all, I think what you need is something that has system-wide visibility. You need to have global scheduling over all of the resources that are available. On top of that, you require low latency coordination for your agentic AI workloads, or indeed any AI workloads. And this sort of means communicating with that without that RPC cost you're seeing in server-centric systems. You also need disaggregated resource pools. This is the term that I'll be leaning into a little bit on this talk. What that means is you can sort of pool resources from different machines together, and effectively they'll coordinate as one. So by resources specifically here, I'm talking about memory, CPU, accelerators, etc. So the foundational technology that really enables this is high bandwidth, low latency fabrics. So think CXL, but in Huawei, we have unified bus, which has been open sourced as a standard as well. This is one of the foundational technologies that allows you to kind of build these disaggregated hardware architectures. Okay, and here, once you have these things, the system itself can actually behave as a single coordinated machine. So now I'm just going to talk to you about how each of these kind of innovations in hardware have kind of enabled what we're going to talk about, which essentially is a superpod architecture. So firstly, on the sort of left-hand side of you here is the old world view, so sort of this bit, and on the right-hand side is kind of like where we're moving towards. So in the left-hand side part, the traditional model, the CPU is at the center of absolutely everything. It coordinates all of the heterogeneous resources and kind of pulls your kind of work onto the GPU through parallelization, etc. Data flows through that host, and you have limited parallel interaction. The CPU is at the center of the universe. The emerging model, which is the disaggregated model, you have, of course, heterogeneous hardware, which is prevalent everywhere now. That means CPU, memory, XPUs, etc. But you have no single center. You have much more like a kind of peer-to-peer, direct-to-direct communication model here, and system-wide parallelism on top of that as well. So there, the system itself, not the individual server, becomes the unit of execution. The next shift that we've seen, a sort of innovation in hardware, is moving from servers to like a unified infrastructure model. This is a little bit like, I've spoken about this a bit already, but in your traditional data center, the resources are pegged to an individual single machine. So this is sort of depicted by the left-hand side here. You have, let's say, CPU, memory, GPUs, etc., that are bound to a single machine. Those resources are tied to those servers, and you have fixed boundaries and local scheduling. The model we're moving towards with disaggregated hardware allows you to pool the different resources together across racks. So what does that mean? What that means is I can pool memory from one machine, CPU from another machine, and GPU from a different machine altogether. And then I can pull these resources directly to kind of form a logical machine that I can then deploy workloads onto. And again, this is facilitated through this high bandwidth interconnect, which actually allows those machines to act as one. The final kind of innovation that facilitates all of this is from messaging to memory. So in the traditional model, again, on the sort of left-hand side here, data is sent as messages always between the components in your system. And each step is that round trip, basically, and the software manages the communication. The model that we're moving towards in disaggregated hardware is the emerging memory model, basically. And data is accessed via essentially memory semantics. What does that mean? That basically means that memory can be read or written to across any of the different nodes inside the device. So any kind of single node can read the memory and write to the memory like a pooled memory system across that rack. And the hardware then manages that communication for you. And the system here then starts to behave as a single machine. So let's pull all of these things together. Huawei's implementation of this is called a superpod. Superpods here have disaggregated pools of NPUs, disaggregated pools of CPUs, of memory, of any other resources as well, like storage. And again, the piece that actually pulls all these things together is this high bandwidth interconnect that has very, very low latency. And in Huawei, this is called unified bus. You can then take one superpod and you can connect that to other superpods, making what we call superclusters. So the OS here must treat that system then as one single device. This is sort of a little bit more detail about what that looks like in practice. So in our A3 Atlas SuperPod, we have 384 NPUs pulled together, 192 CPUs, and those are organized into 8 NPUs and 4 CPUs. And then you have 48 machines of those kind of racked together, and again, facilitated by that interconnect. So as I mentioned, A3 here has 384 NPUs, but there are even bigger machines. The Atlas 950 has over 8,000 NPUs pulled together. And looking forward, we're actually looking at building even bigger machines than this. Okay, so how does this all relate to operating systems? This innovation part that we've been building into is OpenEuler, and how we actually enable this for the next generation of developers. So those of you who maybe have not come across OpenEuler, as I mentioned at the beginning, it's Huawei's open source Linux distribution. Started in 2019 here, and the open source code was sort of emerged, and the committee sort of set up. It was then donated to the Open Atom Foundation, and in China, it secured the top spot in terms of like hardware installations. It's now a leading player in the market. The numbers on these slides are slightly out of date, but 2024 here, we achieved over 5 million installations. That's new installations, and we have sort of 10 million total installations. Moving on to what I was talking about with disaggregated hardware, what we're building on 2026 is to enable this SuperPod architecture through the operating system, the foundational layer that allows those hardware resources to act as one. We also have started applying AI into the operating system itself, and I'll give you a couple of examples of that in a moment. The first version here of the OS that supports this was released late last year, and it's a first step towards realizing that SuperPod implementation. There are updates of this, but only research implementations at this point, but this is one of the latest updates for us. And here we've been moving towards this pooled compute, memory, and accelerators across different racks through the OS. So how specifically have we actually started to meet these requirements here? The stack that we've been developing is kind of 3 logical layers here, and I'll just briefly mention what they are without going into too many details. At the bottom, we've got the disaggregated resource pooling. This is the foundational layer that allows us to do things like unified addressing, high-speed interconnect via UB, pooling of resources, etc. On top of that, we built out coordination for it. So this allows us to do things like memory systems, communication across XPUs, etc., within the rack-based systems. We've then been building kind of the system interface layer as well. And this allows us to pull across the infrastructure, VMs and containers, and splice them over this disaggregated architecture, building out things like global memory systems, global pooling, etc. Some numbers here. Again, I won't spend very long on these because these are really just improvements of OpenEuler itself. But one thing that I find quite interesting from an academic standpoint is the resource utilization argument. So in a traditional cluster, you end up with quite fragmented resources that's called resource stranding. The reason for that is you might have small fragments of CPU, small fragments of memory, which you can never provision a new container over because they're just too small. In a disaggregated model, you don't end up with that. What you end up with is just pulling the exact number of resources that you require for your job, and you don't end up with the resource stranding, and therefore increased overall resource utilization on top. And then we've got different numbers here for inference and training. I think the TLDR here is it also benefits things like inference and large-scale training as well when you have disaggregated pooling of architectures. One of the final things I'll say then is our open source stack, which is called Intelligence Boom. This is our entire open source sort of division here that looks at various levels of the stack and basically facilitates things like task management, runtime acceleration as well. I'll just give you a short couple of examples over each of them. Starting at the bottom here, the heterogeneous convergence layer is mostly about facilitating the hardware. So here we've got things like the compiler, the memory systems, etc. On top of that, for task management, we've got a couple of solutions which have been open sourced quite recently. OpenYanrong is our serverless engine. It is now fully open sourced. Go and check it out. Again, we had a couple of workshops last week where we're sort of demoing this. OpenEuler also builds on Kubernetes, but looks at more specifically large-scale AI clusters as well, and large-scale divisions. On top of that, OpenGauss for database management, again, like an enterprise-grade relational database. Runtime acceleration, Mindspore is our open source AI framework. It provides native support for training, inference, etc. at scale. And then the final piece here is really how you apply AI to the operating system. Here, the thing that I find quite interesting is the things kind of running for agents. We've got something called AI Ops. AI Ops is where essentially you take a large-scale framework, something like Spark. It has hundreds of configuration options when you deploy it, and those configuration options actually matter to the performance of that application. AI Ops will take that and it will automatically configure those for you, so you end up with better utilization, better performance on the underlying hardware. I'll wrap up now. So what I've talked about this afternoon here is essentially how we're shifting in the hardware to support disaggregated data and agentic AI workloads. The data center has become a single programmable system, and communication essentially becomes direct through things like memory semantics and low latency fabrics as well. The OS then becomes the runtime for the agents, and then ultimately your agentic AI workloads will sort of enter better performance when they run on this type of disaggregated hardware, which is not fully prevalent yet in data centers, but is definitely coming. So I'll leave you there. This is OpenEuler. Check it out. Thank you.